Hello. Today I want to talk about the highlights of a physics project for students that was initiated by a Foothill College math instructor. Foothill is a California community college where my co-author, Jeff Anderson, teaches linear algebra. The students intend to transfer to STEM programs in leading four-year universities. This project, using linear algebra and eigenvalue analyses, arose because Jeff hoped to motivate his students about the value of applied math to their future careers and rekindle their commitment to learning what appears to be abstract mathematics. What problem are we addressing? Student complaint: linear algebra is too abstract. So Jeff said, can we do a hands-on student project for modeling of a practical problem, and suggested a spring mass spring system, and then added the requirements. It must be hands-on. It's really a student project. Low cost. Community colleges have very low budgets. Simple construction methods. Portable. Free tools, and open-ended. Very quickly, we identified that the spring mass system requires a low-friction air track. So we suggested changing to a spring-coupled pendulum. These two have effectively the same mass. The normal modes are symmetric movement, the two masses running in the same direction, or the anti-symmetric, the two masses running in exact opposite direction. The normal modes are represented by eigenvectors, and the mixed mode, or the beats, are described by a linear combination of normal modes. So the project: build a pendulum-spring-pendulum system. Today, in the limited time I have, I'll illustrate the apparatus, some of the methods and physics highlights, and very few math details, but links to the math details are at the end. I'll show typical measurements and we highlight motion time capture with a video camera. We use open source software for image analysis, do modeling on a spreadsheet, and I'll provide the materials list that assures that this is very low cost. So here's a system schematic. The frame is a metal shelving. On the top we have plywood that can support two platforms with 4 cables so that the platforms move parallel to themselves. There's a spring connecting the center of mass of the two, and there is a video camera that is located on the top. Again, we measure the motion with a video camera. Here's some photographs of the actual apparatus. It looks a little bit crude, but this is the first article, and it does the job very well. On the left we have the end view, and on the right we have the side view. You can see the cables, the metal cables, plywood on the top, and the two platforms that move parallel to each other. The camera is located such that the focal plane of the camera is parallel to the motion of the platforms. Here are more construction details. On the right we have a top view showing the hole for the camera and slots for the cables just right there. On the left, the white disc, you can see the masses, and the white disc is a labeled CD with a black spot that the software can follow for collecting data. Here are some typical results for the mixed mode measurements and also for the model. On the upper left we have in red the data, and on the lower data for position, and on the lower right we have data for velocity. you can see just hidden away, except for a couple of points, blue is the model that resulted from this activity. Again, the data is collected by tracker software, and this shows the graphics that can be done by Excel, which is accessible to all of the students. Here is an expanded time view of the same points, and we can see that the comparison of the data and the model, again, the camera is 30 frames per second, so this is 33 milliseconds per point. You can see that the consistency and the matching is rather good. So the project activity sequence that we have, we video the position of each moving mass for an extended time. We can choose between modes. We load the video into tracker software, links provided at the last slide. We export. The software provides the data in comma-separate variables. We export that to a spreadsheet for analysis. We develop the model using linear algebra and the result of the measurements. We compare the model to the data, and you can see we have excellent agreement to the data, and we have some degree of student achievement. So going back, this is a typical frame grab from the tracker software. On the left, we have a single image of the 3000 that we measure. The data point that's followed is illustrated there, and you see in the green we have that data is being shown on the upper right as a graphical representation, and on the lower right as the data representation. Here we have time, position, velocity, and acceleration, in this case for the right mass. We export that for the from the CSV into Excel. On the left here we have the left mass, position, and time and velocity, and here we have the right mass. We do the calculations extensively over here. Things you can do: build a system like this. Share the work with a math instructor. There are a variety of activities you can do. Again, the motivation is to add measurement and modeling to math courses, and to me, prepare for eigenvalues in quantum mechanics. Some notes on the equipment, right at the bottom, $100 or much less. And finally, some links to the references. The key one is in red there, appliedlinearalgebra.com.